So this is analog signal sampling and reconstruction, right? So in this experiment, we are going to demonstrate how the analog signal will be sampled and reconstructed at the output, right? So here sampling, already you know what is sampling. Sampling is nothing but it is a process of converting the continuous time signal into discrete time signal, right? Continuous time signal into discrete time signal, that is the sampling process. And for sampling process we are having the signal sampler. In this trainer kit we are having signal sampler, right? Signal sampler, it is a switch, actually it is a switch, and it needs two signals, right? One is input signal, that is modulating signal, a signal which is going to be sampled by the sampling pulse, that is nothing but modulating signal or input signal, right? Analog signal, right? And here actually we are having different frequencies, right? 225 hertz, 250 hertz, then 500 hertz, right? Among these three frequencies, right, you can select any one frequency at a time, and that frequency is applied at the input of signal sampler. Okay, so at this pin you are going to connect the modulating input, right? And we have one more provision, that is sampling input, right? And for this sampling input, right, we need to generate the train of pulses, sampling pulses, right? So for that we are having different circuits, right? Binary counter, multiplexer, BCD counter. Then after that finally from this comparator you will be getting output, sampling pulse output, and this sampling pulse output is applied to the input of signal sampler, right? So sampling input, sampling pulse, right? What is sampling pulse? Sampling pulse is nothing but a pulse which is used to or which is used to actuate the signal sampler, right? Because already you know what is signal sampler. Signal sampler is nothing but switch, right? Signal sampler is nothing but it is a switch, right? So that switch will be actuated with the help of sampling pulse, right? So whenever the sampling pulse is present, this signal switch will be closed, right? So signal this switch will be closed, right? So whenever the switch is closed, the input just reaches the output, right? The inputs just reaches at the output. Whenever the switch is open, there is no output, right? There is no output. Okay, the input does not reach the output. So in this way we are going to convert the continuously varying signal into discretized time signal. Okay, discretized time signal. So at the output of signal sampler we will be having three provisions. One is sampled output. The sampled output is nothing but natural sampling, right? Natural sampling. And the sample and hold output, then flat top output, right? Flat top output. So what is natural sampling? What is sampled output? Here actually the sampled pulse just follows the shape of the input signal, right? Like so this is the model graph, right? So this is original input signal, that is a signal which is going to be sampled by the sampler, that is analog signal. This analog signal will be converted into discretized signal, right? So for that we are going to make use of sampling signal, right? This is a sampling signal or sampling pulse. This is strain of pulses, rectangular pulses, right? Which is used for actuating the sampler switch. Okay. And whenever the pulse is present, this output, this input just reaches the output. That is why you will be having discretized output, and this output is nothing but natural sampled output, because the top of the pulse just follows the shape of the input signal, right? This is input signal. So this is the converted signal, discretized time signal, right? With the help of a signal sampler you are going to discretize the analog signal, right? So after sampling, right, the pulse will be like this. Here the top of the pulse just follows the input shape. That is why it is nothing but natural sampling, right? And now this natural sampling will not be applied for the receiver, because the circuit operation would be complex, right? If you are going to apply this natural sampling for further operations, then the circuit design will be complex. So to avoid that, to simplify the circuit design, we need to convert that varying pulse, varying top portion into flat, right? So that is the flat top sampling, right? That is why it is nothing but flat top sampling. So in flat top sampling, the top of the pulse will be flat, right? How will you get this flat top? With the help of sample and hold circuit, right? With the help of sample and hold circuit. So inside this trainer kit we will be having one more circuit, that is sample and hold output, right? Sample and hold circuit, right? From that output you will be getting sample and hold circuit. What is the main purpose of having this sample and hold circuit? Actually this circuit just takes the sample and it holds the value until the next sample arrives, right? So like that you will be getting staircase waveform, right? So once it takes the sample and it maintains that sample value until the next pulse, right? Similarly, next this circuit takes the sample, and after that it just holds the that value until the next pulse. So in this way you will be getting the flat top sampling, right? Flat top output. Okay, this is flat top sampling, right? So after that, this sample and this flat, you need to calculate, you need to observe these outputs: sample output, sample and hold output, flat top output, and the sampling pulse, then modulating pulse. There are 5 observations in this train circuit, right? These 5 signals must be noted, right? Must be noted, right? Now here actually I am going to measure the sample and sampled output, right? Already connections are made as per the circuit diagram. Now we are going to measure the input signal, right? Input signal. First we have to measure the input signal, right? So I'm going to connect the CRO at the input of a signal sampler, and now the output will be like this, right? So this is the input, this is the original input. Okay, so this is the input signal, original input signal. So for this input signal, for observations, you can have hold off provision in the CRO, right? By adjusting hold off, you can stop the running waveforms, right? So now you have to calculate amplitude as well as time period for this input signal. Okay, so this is the input signal. Next you have to observe the sampling pulse, right? So the CRO is connected at the input of sampling, right? Sampling input, right? Now this pulse is going to be observed in the CRO, right? CRO. So this is the sampling pulse output. Here actually we have train of pulses, right? For this train of pulses, again we need to observe the amplitude as well as time period, right? Next we are going to observe the sampled output. This is natural sampling. So for that you have to connect the CRO at the provision of sampled output, right? So here I am going to connect the CRO. So this is the sampled output, right? Sampled output, right? So the continuous time signal will be converted into discrete time signal, right? So whenever the pulse is present, will be having output, right? This pulse just follows the natural original shape of the original signals. That is why it is nothing but natural sampling, right? Here also you need to calculate how many samples are taken for one cycle, right? So here actually we are going to take 3 samples, right? 1, 2 and 3, right? So 3 samples are taken from the input. That is why you just note down the number of pulses for number of samples per cycle, per half cycle, right? You have to note down. Now we are measuring the flat top output, right? So for that I am going to connect the CRO at this position, right? So flat top sampling, the top of the sampled pulse, right? This is the output, sample and hold circuit output. Here actually the top of the pulse output will be flat, right? Whereas in previous case, that is natural sampling, the sampled pulse just follows the shape of the input signal. Here actually instead of following the shape of the input signal, the top of the pulse, sampled pulse will be flat. Okay, so here also you have to take the reading for number of pulses per cycle, right? How many number of pulses will be present inside the half cycle, and you have to note down the amplitude and the time period, on period as well as off period. Okay, so this is the demodulation, that is reconstruction. So for that now I am going to connect any one sampled signal at the input of reconstruction filter, right? At the input of reconstruction filter. Here actually I am going to connect the natural sample output into the reconstruction filter input, right? Here we have a second order filter, right? That is 2 stages of second order filter. Order is nothing but that number of RC sections, right? So whenever you are going to increase the number of RC sections inside the filter, then you can closely approximate, you can easily approximates the original input, right? So low pass filter, the purpose of having low pass filter is to smoothen the staircase waveform, right? Staircase waveform. So if you are going to increase the number of orders of the filter, then you can get the exactly original input signal at the reconstructed output, right, at the receiver side. Okay, so here actually the first stage output is connected to the second stage input, and finally you are going to take the output from the second stage, right? So second stage now I am going to connect the CRO, and after connecting, this is the reconstructed output. We will be getting reconstructed output at the output. So this reconstructed output is the original analog signal, right? Original analog signal. Here also you are going to take the amplitude as well as time period for the graph. Okay, so this is the observation table, this is model graph, and this is observation table. So for observation table, we have to mark the amplitude and the time period of all the signals, and you have to plot the respective graphs. This is what the signal sampling and reconstruction, right? Signal, this is what because at the receiver transmitter side, the modulating signal is applied to the signal sampler, and it is sampled by the sampler, and finally this sampled signal is applied to the receiver side filter, and this reconstruction filter reconstructs the original information. This is what sampling is done and reconstruction is done with the help of transistors, right? That's all about signal sampling and reconstruction. Thank you.